So in previous classes, we discussed about series resonant circuit and a parallel resonant circuit. Okay. So as we are aware that, so these resonant circuits are applications like especially induction heating. You may have seen that induction heaters are there, right? Or induction cooking tops are there. Okay. So in that, so these resonant circuits are used, and also applications like wireless chargers. We have some battery chargers are there, so that are coming with you. Some, if you observe that the mobile phones are coming with wireless charging. Okay, so on the back of their on the back panel, okay, so we have some coil will be there. So that coil is capable of this wireless power transfer, and also we have reverse wireless charging is also there. Okay, so that means the device, the mobile phone itself will charge the another mobile or any other some Bluetooth devices or something like that. Okay. So these are some of the applications of these resonant circuits in day-to-day life. Okay, now we'll try to solve some problems on this resonant circuits. So in previous classes, we discussed about the series resonant circuit and we solved some problems. So now we'll solve some problems on parallel resonant circuits. Okay. So let us assume that we have some circuit like this. Right. So for this circuit, if you fix the resonant frequency at 1 kilohertz, resonant frequency at 1 kilohertz, calculate the value of L. So you fixed the resonant frequency. So now you need to calculate the value of L. So how to solve this one? How to solve this kind of problems? Either, okay, either you calculate the inductance, either you calculate the admittance of this total circuit. So calculate the admittance of this total circuit and equate the imaginary part to 0. Okay, so equate the imaginary part to 0. So that gives you the answer, right? So that gives you the answer. Or, so what is the other way? So we calculate the admittance of this circuit. So what will be the admittance? Can anyone tell? So what will be the admittance of this circuit?
Sir, imaginary part can I told?
Yeah. So it will be 3 by, okay, 3 square plus XL square, okay, minus J into XL by 3 square plus XL square. So this is for this one. Similarly, what is the other one?
Sir, 4 upon 116
4 upon 116 minus
plus J10
plus J10
J10
by
by
416. Okay. So if you solve this one, so you will get a quadratic equation in terms of XL square, right? Or in terms of XL square. What is that? What is that quadratic equation? So we need to equate the imaginary part to 0. So what is the imaginary part here? What is the imaginary part? 10 by 116 minus XL by 3 square plus XL square. So this is equal to 0, right? So this is the imaginary part.
Sir, quadratic equation is 10xl square minus 116xl plus 90 equals to 0.
So that means XL square minus, what is that? 11.6
6xl
plus,
plus 9
okay.
is equals to 0.
So what are the roots for this? So what are the roots for this?
Sir, two possibilities is there.
Yeah, okay. What
First
are
is sir,
those?
116 plus 99.27 by 20.
What are those final values?
50.47.
Mm-hmm.
50.47.
30,
50.47.
50.47
47.
XL.
Sir,
Yes, sir.
10.76.
No, yeah, 10.765,
0.83.
0.836.
0.83.
836.
Yeah, okay. So this is value of XL, right? This problem is not over yet, right? So what is the value of L? So XL, you know, to your right. So resonant frequency, you know. So from that you calculate the value. It will be 10.765 divided by, okay, 2 pi into frequency is 1000, right? So this is the value of 1L. Similarly, L2 0.836 divided by 2 pi into 1000.
Sir, L1 is 1.71 millihenry.
1.71 millihenry. Okay. So 1.71 millihenry, one option. Another option is
Sir, 0.133 millihenry.
0.33 or 13.
Sorry, 0.133.
Okay. Millihenry. 1.13 millihenry. Sorry, 0.13 millihenry. So these two are the options. Okay. So remember, sometimes what will happen if you
0.133 milliamps.
0.133, yeah. Okay. So sometimes you will get a negative values, for example, negative values of L. So that indicates that, so those are not valid ones, right? Okay. So those are not valid ones. We have to, we don't consider those. Okay. So don't make it positive and consider that. Okay. So that means you are getting a negative values means, so that is not the correct, so the correct options to pick up, right? So only positive ones we need to consider. So try solving this problem. A coil of inductance 120 millihenry. A coil of inductance 120 millihenry and resistance are equal to 150 ohm. A coil having inductance of 120 millihenry and resistance of 150 ohm is connected in parallel with a variable capacitor across 20 volts 4 kHz supply.
What is the supply?
20 volts 4 kHz supply. So what is the circuit? So we have the coil is given, right? The coil, these things means what is these things two are in series or parallel? This L and R are series or parallel? Series, right? So that is they're talking about a capacitor is in parallel with a coil. Okay, so this is coil, right? So this coil is having a resistance of 150 ohm, inductance of 120 millihenry, right? So that means the circuit can be drawn like this. So we have a capacitor here, a variable capacitor, and a resistor. So this represents the coil, right? So this is 150 ohm here, and this is 120 millihenry. So this is C, and this is 20 volts for kilohertz, right? So determine for the condition where the supply current is minimum. Determine for the condition when the supply current is minimum. The first one, C, capacitance of the capacitor. So that is C, capacitance of the capacitor, C, dynamic resistance RD, supply current, I, here you have I, Q factor, bandwidth, upper and lower minus 3 dB frequencies, upper and lower minus 3 dB frequencies, the value of circuit impedance, at minus 3 dB frequency. At minus 3 dB frequencies. So all these things you need to calculate at resonant frequency, so which is given as 4 kilohertz. Right? One second.
Condition of the supply current is minimum.
Yeah, so that means it is resonant frequency, right?
लेकिन आवाज नहीं आ रही पढ़ता फिर बैठ के क्या फायदा रे बुक्का लेके लिखने का भूलिस गया बोले तो बुक्का
Turn off your
बैठ
mic.
लिखा
Okay. See, this is the circuit. So what is the resonant frequency? What is the resonant frequency if this is the circuit?
4 kilohertz.
4 kilohertz.
No, we have formula, right? What is that formula?
1 by root under
1 by square root under 2 pi
LC.
square root
1 by
1
LC
by
1 by
LC
LC minus
minus R
R
square
square
by
by
Divided by L square.
L
L
square.
square.
Okay. So in the same case, in the previous problem also, we have some formula, right? Okay. So instead of that, you can also use the formula. So what is that formula? What is the resonant frequency formula here?
So 1 upon 2 pi into under root LYC minus R square upon L
What is
square.
that?
One
What
by
is
2
that
pi
here?
into root over LC into root over RL square minus L by C
Root
by
over
R
LC into
minus L by
minus
C.
root over LC minus.
Sir,
Yes.
sir, in denominator root under LC and into
Wait. It is root over LC
LC.
here, right? Okay.
Yes, sir.
So you will get RL square minus L by C.
L
I
by
think.
C.
RC square minus L by C. Okay. Straight away you can use this formula also and equate this to 1 kilohertz so that you will get the answer. Okay.
Sir, won't there be, sir, in the previous page, won't there be a root for RL square minus L by C by RC square minus L by C part?
Yeah, this is root is there. Okay. We derived no this expression. Right. So root is there. Okay. So here, so now tell me, so what is the value of FR is given, right? So this is 4 kilohertz. So from this, you need to calculate the C value. So what is C?
C is equals to 13.16 nanofarad.
13.16 nanofarad.
Nanofarad. Yes, sir.
Okay. Nanofarad means 10 to the power of
Minus 9.
minus 9. Okay.
Yes, sir.
10 to
Yes,
the
sir.
power of minus 9, right? Okay. So next thing, what is the next question? What is the second thing? RD, right? What is dynamic resistance RD formula?
So L upon CR.
L upon CR. So calculate this one.
61.5 kilo ohms.
61.5. Is this correct?
Yes, so 60.7 kilo.
60.7
So 60.7 kilo ohm.
kilo ohm. Yeah, correct. So third one. So what is the supply current I? What is I? So this one now will become IR, right? So that means resonant current. So what is this? How much is this? What is the formula for this IR? If you know the value of RD.
So V into
V
IR,
upon
sir.
V into IR. Is this correct?
So
sir, V
YR.
by RD.
V by
20.
RD,
RD.
right? Just simple. That is the resistance of the circuit, right? In other words, that is the impedance of the circuit. So this is the impedance of the circuit, right? So this is simply V by RD only. So what is this value? V is 20, right? 20 by 60.79. What is this value?
0.329 milliampere.
0.329 milliamperes.
Yes, sir.
Okay, yeah. So next fourth one, what is Q factor? Q factor,
Omega R
Q
upon
R,
L.
Q at resonance, right? Omega R, L by R, right? So calculate this one. So 2 pi into 4000, right? Into L. L is 120 into 10 to the power of minus 3. R is 150 ohm. So what is this value? For this, there is
2.09 into 10 to the power 5.
10 to the power of 5, that much.
Sir, 20.1 is up. Yes, sir,
It will be 10 to, not in the order of 20, 10 to the power of 5 or something.
20.09, sir.
Hmm?
20.1. 20.
Yeah, 20.1. So here there is no units for this one. Okay. So you can also use the alternative formulas 1 by omega R RC, right? So this is one formula, right?
Yes, sir.
Agree? Or you can also use 1 by R square root L by C. So this also you can use. Understood? Okay. So next one, fifth one, bandwidth. What is bandwidth? How to calculate the bandwidth?
Sir, FR upon QR, sir.
Yeah, FR upon QR.
So 199.
199, sir.
199 hertz or kilohertz? Hertz only, I think.
So hertz.
So sixth, upper and lower 3 dB frequencies. Upper and lower 3 dB frequencies, right? So how to calculate this one? Or else we can roughly estimate these values also, right? You can roughly estimate these values. So what you will get if you roughly estimate these values?
Sir, if we assume 200, then 4,100
Yeah, 4100
is
upper
F2.
frequency and the lower one is 3900 in hertz. Just calculate this one whether it is same or not. You're supposed to get 200 because of this some points variation, some decimal point variations. So that's why you may getting on 199. Okay. So this can be this is the estimated one. So FR equal to square root F1 F2, right? FR equal to square root F1 F2. We also given the another one is F2 minus F1 is 199. So this is another relation, right? Okay. So from this, right, you need to formulate a quadratic equation. You need to formulate a quadratic equation. So from that you can solve for F1 and F2. You can solve
So
for
it will be 3800, sir.
why 3800? This one. This is the one you're talking
Yes.
about. Why
Yes,
38?
sir.
Can you tell me why 38? See here, F2 minus
Bandwidth, sir.
F1 is supposed to be 199 hertz, right? In that case, if it is 38, it is obviously 300 hertz. So that is wrong. So bandwidth is given, right? So that is around 200 hertz we are assuming. So that is equally distributed. So here this is the bandwidth. Okay, so this is 200. So this is the center frequency 4000. So how to equally distribute? Simple sense. So this is 3900 here and this is 4100 here. That's all, right? Understood?
Yes, sir.
Still confusion? If you want precisely, right, you need to solve these two equations, fr equal to square root f1 f2 minus f1 equal to 199 Hz. Okay, so more or less you will got the same answers, more or less you will got the same answer, or you have some formulas also there, right? So that also use f1 f2, we have some formulas there. Okay, so that also you can use. So next one.
Sir,
Yes.
so with that estimation, we are getting FRS 399. So with that estimation, without calculating, we are getting FRS 3999.
3,999.
399. Yes, sir.
What is the resonant frequency is 4000 Hz then? Will it be the case? 3,999 is one less than the resonant frequency, right?
Yes,
That means
sir.
somewhere you did some mistake.
No, sir. Calculation wise, also needed values have come like 4100.735,
Yeah,
3900.735.
yeah, that will. Okay, so not this one. Okay, you will not get 3,999. This is the one you are saying.
Yes, sir.
This is the one 3,999 Hz. No. So absolutely this is wrong. Okay? Because the resonant frequency itself 4000, right? Okay, so it can't be same if this is the difference. Okay, so just try to solve it correctly. Next one, the value of circuit impedance at minus 3 dB frequency. Okay.
Sir,
What is
root
the
2
answer?
upon RD.
Sir,
Root
RD
2
by
upon
root 2, na?
root 2 upon RD. No.
RD by root 2, sir. Inverse of
Yeah,
reciprocal
RD
of
by root.
YR.
No. Wait. So the impedance of the circuit ZR. What is the impedance of the circuit ZR?
1 upon YR.
1 upon YR. So what is this 1 upon YR? What is the impedance of this ZR? What is this then?
RD.
Okay.
RD, sir.
So this is impedance of the circuit, right? Okay, but why we are naming that as a dynamic resistance? Because this is depends on the resonant frequency, right? So that's why we are named it as a dynamic resistance. Okay, so this ZR equal to 1 by R. In other words, this ZR equal to RD. Agree? This ZR equal to RD, right? This you understood?
Yes,
So
sir.
this is the maximum resistance or minimum resistance. In
Sir,
parallel
maximum.
resonant
Maximum
circuit,
resistance.
some parallel resonant circuit, the admittance is minimum. That means the impedance is maximum. So this is the maximum possible impedance, right? So that means the curve will be something like this. So this is RD. Okay, so now what is this one that they are asking, right? So what is the value of this one? So this is the maximum resistance. This is RD, right? So what is the value here? So this is obviously RD by root 2. RD by root 2. So this is impedance of the circuit at F1 or F2. Impedance of the circuit at F1 or F2. So that is RD by root 2.
While calculating F1 and F2
Yeah.
in sixth question,
Mm.
we can take F1 and F2 symmetric about FR in every case, or only when QR is greater than 10, something like that.
See here, okay, the good question. Actually, if QR is greater than 10, right? So the difference between the symmetrical, it's almost symmetrically placed, right? If the QR value is, for example, 1.5 or 1.5 or 1.2, so in that case, so our prediction may be wrong. Okay, our prediction may be wrong.
Okay, sir. Then
So
we
in
need
this
to
case,
calculate
obviously this
exactly.
QR is greater than 10, right? So that's why, so these values are more or less equally placed.
Okay, sir. Got it.
So what is the answer for this? Seventh question.
So 42.92 kilo ohm.
42.92. Yes.
Sir, once again, can you explain why circuit impedance is RD by root 2 again?
This is the one we explained, right? No. So this is the, what is this? This is the maximum possible impedance, right? Agree? Okay. So this is the maximum possible impedance of the circuit. So from this, so that means this is the maximum possible impedance. So this is, you have RD here. So here you have this F1 here and here F2 here. Right. So what is the value of this one? What is the value of this one? So it is obviously RD by root 2, right? So this is also RD by root 2. That's all. So this is the curve we drawn, right? So this is with respect to FT and this is Z. Understood?
Sir, I saw. Why did we take RD by root 2 as circuit impedance, sir?
Yeah. Hmm. Why we
Means
take as?
RD by root 2 as circuit impedance.
Yes, RD by root is circuit impedance at minus 3 dB frequency.
Minus 3 dB is means we should convert no sir in logs. That formula is there.
No, you are missing some classes, it seems. Right. So here minus 3 dB means, okay, so we assume that the upper and lower off power frequencies F1 and F2. So there is a other name for this one is minus 3 dB frequency. In one of the class we discussed this. Okay, no need to do the conversion and all.
Oh, okay, sir.
Okay.
Okay, sir.
So note down another problem. I think I have one doubt. Is this curve correct? This curve. In one of the class we discussed this. Is this curve correct with respect to the
Yes, sir.
parallel resonance? Huh?
Yes, sir.
Okay, this is with admittance. Okay, so then it is correct. Okay. Now I got it. So this is admittance, and this is for I think that day we discussed about. So this is for parallel resonance, and this is for series resonance, right? Yeah, now
Yes,
I
sir.
got it. I thought I have drawn in the other way. Okay, so now down another problem. In a RL C network, in a RL C network, the capacitance C is 10.61 nanofarad. Bandwidth is 500 Hz. The resonant frequency is 150 kilohertz. Determine Q factor Q factor, dynamic resistance RD, magnitude of impedance of the circuit, impedance of the circuit when the supply frequency is 0.4% greater than tuned frequency, 0.4% greater than the tuned frequency. This is the first, second, third, right? Okay. What is the first one? What is the first one? What is the answer for first one? Q factor, right? So how
300.
Q
300.
factor?
300.
Hmm. It is
300.
what is FR is given, right? So bandwidth, right? So how much this is? 300.
Yes, sir.
So next question. What is RD? Dynamic resistance. You need to calculate, right? What is this value? RD formula. It is L by CR, right? L by CR. So now, is these values are given? Is these values are given?
No, sir.
L is not known to you, right? And C is also not known to you. So now tell me how to calculate this.
Sir,
RD
QR
sir.
is equal to
Oh my.
1 upon omega R CR, sir. So from there, sir, we can calculate the value of R.
Yeah. So we had different ways to express this QR, right? So this QR can be expressed as, okay, one way is omega R into L by R, right? Okay. Is this correct? Omega R into L by R. Agree? So if you notice that, so this is L by R, right? So this can be written as 1 by C into L by R. Understood? Tell me if I'm wrong. Is this correct?
Yes, sir.
Okay. So what is 1 by C? What is L by R here? So from this, what is L by R? So from this, L by R is? What is L by R?
QR
So
by
with this, what is L
omega
by R? QR by omega R, right? So this can be written as, this L by R can be written as QR by omega R. So from this, RD can be written as QR by C into omega R. Is this correct? Did I made any mistake? I think this is correct. Correct, no?
Correct, sir.
Yes,
Okay.
sir.
So what is the answer then?
29.97 mega
How
ohms.
much? How much?
29.97.
20?
9.97.
29.9 kilohertz or hertz? A kilo ohm or ohm?
Sir, mega ohm.
Mega ohm.
Yes, sir. Capacitor is in nano farads, sir.
It is kilo ohm. No?
Nano means 10 to the power of minus 9, you consider.
Yes, sir.
Sir, 30 kilo ohm.
So
Kilo
30
ohm.
mega ohm is there.
30?
Mega ohm.
Kilo ohms.
It
Sir,
is
30.3,
0.03
sir, kilo ohm, sir.
Kilo ohm. Kilo ohm.
Yes, sir.
Okay. I think nano, you're supposed to consider 10 to the power of minus 9. Okay. That's why you may be getting wrong ones. All right. What is the next thing? What is the C or the third one? Magnitude of impedance of the circuit when the supply frequency is 0.4% greater than the tuned frequency, right? So now what is the formula of Z or Z by ZR? What is Z by ZR?
So 1 plus J2Q delta.
Z by ZR.
1 by 1 plus J2
1
delta
by 1
Q.
plus J 2
No, sir.
delta.
In numerator, this value. Sir, I by IR is 1 upon 1 plus 2
No, we
J2 delta
derived
Q.
that day. Wait a second. Yeah, I by IR equal to 1 by J into 2 delta IR, right? So what is the value of I?
So Z by ZR will be reciprocal of this now.
Yes, sir.
This is Z by ZR. No, this is for
Sir, Y by YR equals to 1 plus J2 delta QR.
just a second. Yeah, Z by ZR equal to this is the one.
Sir, greater than means we have to take positive, no, sir?
Yeah, positive only. No, I think 1 second, 1 second.
We should, because F2 is more, it is for the positive frequency.
So I think there is some mistake here. I think. Okay. So this is Y by YR, right? So Y by YR is, so this much, right? Agree? 1 by 1 plus J into 2 QR, right? Okay. So if this is Y by YR, I think, right. So what is this correct?
It will become reciprocal, so Z
This
by
will
ZR
become
equals to
reciprocal,
1 by.
right?
Yes.
That day we did this.
We derived the Y by
mistake.
YR. Sir.
So we derived Y by YR, right? Okay. So this Y by YR. So this is equal to 1 plus J 2 delta QR. Listen everyone. So y by yr is, so this is the one, right? So this is the one. So accordingly, so what is z by zr? So now what is z by zr? So reciprocal
So
of
one
this one.
upon
1 upon j
One,
to
one, plus
delta q. Please change this one. So that day we made this mistake.
Sir,
Yes.
sir, that day,
in
sir, we
I
didn't make any
formula
mistake, sir.
V
So
upon
that
impedance, na?
Yeah, what you
Sir,
say?
sir, in the formula of I, means current, it is a V upon Z, na? Means impedance.
Yeah.
yes, sir.
Sir,
With
then if I replace the I with Z by V
No,
by
no,
Z,
we
and
will see. This is wrong. The rest of the things are also wrong. So this is the original one, right? Okay. And original one, and this is correct. So y
sir,
by yr, so which is equal to 1 by j 2 delta qr. We'll start from here. Okay, honestly. So this is the one.
sir,
Yes, 1 second, please. Don't confuse me. 2 delta qr. Okay. So this is the one that we got. Okay, we'll compare with the so this is in case of, so this is parallel resonance, right? So this is in case of series resonance. So this is Z by ZR, so which is equal to 1 plus J2 delta QR, right? Agree? So this is series resonance.
yes,
Just
sir.
check this one. This is series resonance related, right?
Yes, sir.
Okay. So that means if this is series resonance, the parallel resonance will be something like this, right? Agree?
Yes, sir.
Okay. So now tell me, okay, just keep that aside. So now tell me what is Z by ZR? What is Z by
So
ZR?
1 upon 1 plus J2 Q delta R.
1 upon 1 plus J2 delta QR, right? So whereas here, so this is Z by ZR. So that is the thing. Understood? So here I by IR is, what is I by IR here? I think 1 by 1 plus J2 delta QR. Is this correct?
Yes, sir.
Okay. So now what is I by IR here?
1
What
plus
is I by
J2 delta
IR?
QR.
1 plus J2 delta QR.
Same
1
formula.
plus J2 delta QR. Okay. And once again, this is parallel resonance and this is series resonance. Understood?
yes, sir.
Please change this
Yes,
one.
sir.
The day
So that day, sir, you said you were just comparing, sir. That is why you wrote that expression, sir.
is this.
Yes, sir.
Then why you all said this is the formula then? Okay. Why you all said this is the formula then? Okay. No. Everyone said what is the formula for Z by ZR? So now tell me what is the formula for Z by ZR? Is this correct now?
Yes, sir. Correct, sir.
Yes, sir.
Yes, sir.
Just remember this one, okay? Right. So this is confusing for you and this is confusing for me as well. I don't remember at what contest we discussed this one. I don't know what contest we discussed this one, that I don't remember whether I comparing with the series resonance. Okay. Or I don't know what contest we're discussing. So just to avoid the confusion, so these are the things. Okay. Understood? So now tell me, so this is when I come to this problem, so this Z by ZR equal to 1 by J2 delta QR, right? So this is the one, right?
Yes, sir.
So now what is delta here? So it's said that this is above the greater than, right? So that above the greater than means this is positive only. If it is below the supply frequency means, so this sign will be negative, right? No confusion, right? For this. Understood? So what is delta now? They're given as 0.4, right? So that means 0.0, that means 0.04, right?
Yes, sir. 0, 0.
It's corresponding to 0.4%.
Yes, sir.
Okay. So substitute all the values and tell me the value of Z.
Sir, here you said it will be minus.
Why minus? It is above the resonant frequency, right?
Yes, sir.
No, see here, don't confuse again. So this is greater than, right? So the greater than means plus sign. Lesser than means lesser than the resonant frequency means minus sign. Okay.
Yes, sir. So 790.3 ohm it is coming.
7.
So 790.3 ohm.
Just wait a second, I will check the answer. No. It is around 11.5. Yeah, 11.54 at an angle minus 67.38 kilo ohm.
Kilo ohm, sir.
Okay. That is the one. So that means it is 11.54 kilo ohm. 11.54 kilo ohm.
Sir,
Yes.
sir means in the answer we are considering only magnitude value, na?
Yeah, if it is given the magnitude of the impedance means it is supposed to be. See here, you can see here, right? The dynamic resistance is supposed to be 30 kilohertz. So when the resonant frequency is 150 kilohertz, right? Agree? Okay. So, but there is a small deviation in the resonant frequency. With the deviation, see how the impedance is changed. Okay. So this how this impedance is changed, you can see, right? So instead of 30 kilo ohm, right now the impedance is, so this is the maximum possible impedance, right? So this is the maximum possible impedance, but there is a small change in the resonant frequency. So now it is 11.54 kilo ohm only. So that is reduced. So how there is some problems may ask. So how much percentage of that resonant how much percentage of that impedance is reduced? It will be the questions. It's 30 minus 11.54 divided by 30. Okay. So this is the percentage of reduction in the impedance corresponding to 0.4 percentage of frequency change. Understood? Understood. So we have frequency change of this 0.4%, right? So corresponding change in the impedance is 30%. This earlier is 30 kilo ohm. So now it is 11.54 kilo ohm. So 30 minus 11.54 divided by 30. So that gives you the frequency, that gives you the impedance change. Okay. Okay, we'll stop here in next class. Right. We will discuss some